Okay, good morning, everyone. Today, Marianic is the co-host, so if you're in the waiting room, she will let you in. And also, she is monitoring the chat. Just a remark about the assignment. Um, assignment one, that is. So about 13 of you have sent me your self-assessed grades, which you did by looking at my solutions and your assignment and sending me grades. So I don't know, some of you probably think I was joking about that, but I'm dead serious. This is how you're getting your marks. If you don't send me a grade, that's it, you'll get 0. So of course, the grade you send is just not automatically what I give you, but it is the basis on which I will look at your assignment. So I'll take a quick look, and if it looks like you've graded it fairly, then I will just give you that mark. Some of you are grading yourself a bit too harshly, actually, so I may increase your marks. I don't know what this reveals about your psychology, but anyway, for some people may get their marks raised, some may get it lowered. Other people are, of course, seem to think that everything they've written is amazingly wonderful. So I do need to look at it. Michael is doing rigorous grading of like sampled questions. So he's checking in detail everybody's solution to question 7. And I have not recently looked on the internet for solutions to question 7, but I will do that soon just to see how similar it is to solutions you guys have turned in. A surprising number of people did it. So I must say I'm very impressed, since before that, as I said, 2 people did it in about 15 years. Of course, when it's not an assigned question, people are not so, willing to try it. Okay, we have a lot to do today, a lot.
I just have a quick question on the chat. By when do we have to give you the grade?
Thursday night.
Okay.
Okay, so today we're going to talk about bisimulation. I think I'm going to take off this hoodie. You were expecting to see a big S on my chest? No. Hello? Okay. The joys of teaching from home. You get automated messages from Gaz Metro Plus. Right. Okay. So what we're going to study today is a very important topic close to my heart called bisimulation. Simulation. This is becoming increasingly important, yet it doesn't seem to be included in most courses that you will find in North America. And so it's treated as an advanced topic, but it's kind of a basic topic. The whole point is to move to transition systems as models. Of software or hardware or embedded systems. So unlike when we studied DFA as simple recognizers, which was the right way to approach the algebra of these things, transition systems are more general than that, and they're intended just to study stuff that might be implemented, video games, for example, menus on a website, communication protocols, concurrent programs interacting through shared memory. All these kinds of things are examples of transition systems that people would like to model and reason about. So the transition systems I'm going to introduce today are extremely simple and have minimal structure. So usually one enriches them with all kinds of things. So you can have transition systems with real-time features and clocks, transition systems with probabilistic transitions. And of course, the latter are very, very important in areas like machine learning and optimization, where they are called Markov decision processes. So all these things are under the general rubric of transition systems. So the ones we're going to have study today don't have real time, don't have probability. They're just very basic things. But what they do feature is non-determinism. And they need not be finite state. So we already got a flavor of this from our study of temporal logic yesterday. But today we're going to study this concept called bisimulation, which is all about when are two systems observably the same. So of course, that depends partly on what are you observing. So we will answer all these questions. So the original concept of observational equivalence was due to Robin Milner. But he formulated it in somewhat of a clunky way, though he had the right idea. And he had a friend called David Park who was getting some repairs done on his house. So David Park moved into Robin's house for a few weeks. And so they would have breakfast together every morning. And Robin explained all about his theory of observational equivalence. And David Park realized the right way to formalize this was using fixed point theory. So the modern definition is due to David Park. This got extended to probabilistic systems by Kim Larsen, who's Danish, and his sidekick Arne Skow in 1989, thereabouts, and then to probabilistic systems with continuous state spaces by José de Arnay, Abbas Edalat, and me. And sometime after that, extended to MDPs by Given and Dean. So this was 97. Given and Dean was 03. So Given and Dean did it for MDPs on discrete spaces, not on continuous spaces. So the kind of technical thing that we did did not reach the MDP world until 05, when it was done by Ferns, Precup, and me in '05. Okay, enough history. Let's get, well, let's get on. So let me start with an example first and try and capture this notion of equivalence of two system behaviors. So let's say we have a vending machine. This particular example is due to Robin Milner. Robin Milner ultimately was awarded the Turing Prize for his contributions. So he did fundamental contributions to the theory of concurrency, process algebra, the concept of bisimulation. He also made fundamental contributions to programming languages. He invented ML, from which all those other ML-like languages descended. Okay, so vending machines. So let's say we have a vending machine which dispenses either coffee or tea. I used to say Coke or Pepsi, but I realized it's very unusual to have a machine that will have both Coke and Pepsi in it. So let's say we have a machine that dispenses coffee or tea, and each one costs $1. So we're modeling the system like this. We will say there's a start state, and then you see, what does the machine allow? It has an interface. So what does this interface consist of? There's a slot into which you can insert a coin, and then there's a button which you can press to make your choice, maybe two buttons, one for the coffee and one for the tea, and then it will dispense the thing that you requested. And this output of the coffee or the tea, I'm not going to model, but presumably the person using the machine puts a cup there and receives the, the, the beverage. But you see, in the very first step, the only thing you can do is put in a coin. So we'll model it like that. You ask for coffee or tea, it'll just, the button won't go down. So those actions are not even enabled. So here's a concept we didn't have in automata theory. You can't do any input in any state. Some inputs get rejected. Okay, so this is already a difference. Now that you've put in the money, the machine will say, okay, you can press the coffee button, and then you will get into a state where coffee is output. And in any realistic machine, you then reset back to the start state so that the next customer can use it. But let's just focus on one transaction, and after that, we pretend the machine shuts down, because that is already enough to illustrate the key property. There's a T button marked T, you press it, and you get T output. So if you ask, what are the possible behaviors of your interaction with the machine? So Robin Milner had in mind modeling interactive systems. So he had this idea that machines consist of buttons that you can, as the outside environment, you can press those buttons. And then you see, how does the system react to those external actions? Okay, so if we look at this and we say, let us study the possible behaviors. So this machine has very simple behaviors. You have $1 and then coffee, or $1 and then tea, and nothing else is allowed. You can't have either coffee or tea before you put in the dollar. You could have $1 and then nothing if you don't press the button, but let's look at complete behaviors, i.e. where you have finished the whole thing and gone to the end. Okay, good. So everybody clear about the model and the notion of transition system, which I'm drawing in a picture and which I'll formalize with appropriate Greek letters in a minute? Yeah, good. So let's look at a similar machine designed in, let's say, a dictatorship somewhere, unnamed. And they read the spec which you've given. You said, I want the machine to have this behavior. So we'll say this is the behavior. or the set of possible behaviors. So this variant machine looks like this. You put in the dollar, and it features non-determinism. So instead of going to one unique state once you specify an action, it says, yeah, I can do this or that. Okay, so there's internal non-determinism in these transition systems, analogously to the way we had them in NFAs, except in NFAs, that was a computational model of how to describe a certain regular expression. Here we're saying this is how the system actually behaves. So this means you put in a dollar and some internal mechanism fires up and it makes some choice that you don't control. This is the key point, you don't control it. After that, you see it has these actions. With coffee being dispensed there and coffee being dispensed here. Now you look at this and you say, okay, what are the possible behaviors of this machine? And you say, well, one thing you could do is have a dollar and then coffee. Or you could have a dollar and then tea. Yep. And then you say, now, would you be happy with this machine if what you had ordered was the other one? So the answer is certainly not, or at least I hope not. Because what this machine is doing is it's saying, I'm deciding whether you get coffee or tea. And in this machine, you put in your money and you, the outside experimenter, the outside agent gets a choice. So this is called an external choice. The external agent gets to choose. Both actions are enabled. The external agent chooses which of these actions. This is called internal choice. The machine has somehow automatically decided, and once it comes there, you're getting coffee. Doesn't matter what you might have wanted. Okay? And yet, so clearly these are not the same thing. These are very different, in fact. Yet, if we look at their behaviors, they are absolutely not the same. So, sequences are an inadequate description of the behavior. So what's the adequate description? So very many people thought about this. And one approach is, so what is a good description of behavior? Of behavioral equivalence. And there, the answer of Milner and Park was bisimulation. And one of the reasons why old-fashioned weak one automata theory is not working for us is there's this notion of rejection of an action. You attempt to do one thing and the machine says, no, I'm not doing that, which of course we didn't have in our DFAs. Of course, we had that in our NFAs, but that was kind of a convenience because you could have always said, well, what's really happening when you have a rejected action in an NFA is actually going to a state from which you cannot escape. So you can always convert an NFA into one in which every action is always enabled without making any difference. But here, rejection is an observable thing, and you're seeing the difference in the behavior. And here you see, you put in the dollar, you might come here and then find the T request for T is rejected. So let me formalize a labeled transition system. So I used this word yesterday, but I'm going to slim it down a little. I'm going to take out the atomic propositions and stuff. It's just going to focus on actions. Now, you can make richer models of LTSs with atomic propositions, and you can extend the notion of bisimulation, but I want to have the simplest possible definition because it's already going to reveal all the complexity of the theory. Okay, so definition of an LTS. So you have S, a set of states, perhaps infinite. A set of actions. And this is finite. And then an arrow, which is the transition relation. So this is a subset of S cross A cross S. And the notation we'll use is S. So from state S, if action A is performed, you can end up in S prime. Okay, so I emphasize it's can end up in, not must end up in. It's a non-deterministic system, so you could go to several places. So you don't go to several places concurrently, you make a choice of one of them. So that's why we say you can end up in S prime, maybe you end up somewhere else. Okay, so you can easily see that both these things are examples of labeled transition systems in the sense that I've just described. So now I'm going to give you the technical definition of bisimulation. So now is a very good time to stop me if there's anything about the model you're unclear about. Everybody's good? Okay, let's go. So I'm calling it semi-formal because it's got one part that needs to be made precise later, but it's good to do it in these two stages rather than unload the formal definition on you right at once. So I understand that the Math Society and the Computer Science Society organize this annual party called the semi-formal. So this will be like that. People will be kind of all dressed up, but they'll have drunk a little too much and may not be behaving perfectly. So there'll be something that needs to be cleaned up at the end of this definition. Okay, so another point, I talked about comparing two systems, but for technical convenience, it is easier to talk about comparing two states of one system. It's not a big deal because I can take my two systems, just take the disjoint union and call it one system, and then say I'm comparing these two states of that one system. All right? So what I'll actually define is a binary relation between the states of one system. Clear? So we say S and T in S are bisimilar. if, okay, maybe I should say something else. Written S bisimilar to T if for every A in A, S can take an A action to S prime. So remember, this means can take implies there exists T prime such that T can take an A action to T prime and S prime is bisimilar to T prime. And for every A in A, if T can take an A action to T prime, it implies there exists S prime such that S can do an A action to S prime and S prime bisimilar to T prime. Okay, so this thing will always be symmetric in this way. If S, basically it says if S can do something, T can do the same thing. And of course, you'll end up in different states, perhaps, but those two states will themselves be bisimilar. Okay, so anybody uncomfortable about any aspect of this definition? I'm hoping for a yes answer.
Denali and Owen said yes.
Yes, and what are they uncomfortable about? You can turn on your mics and tell me.
In the base case, there's like, how do you know that S prime and T prime are similar?
Fantastic insight. Okay, so this is exactly what is troublesome. And I'm not going to fix it by putting in a base case. So first of all, this definition needs to be made watertight. There are 4 ways of clearing up clarifying this. And I'm going to tell you all 4 of them. So here we go. So approach 1. We define an n-indexed family of relations. In fact, of equivalence relations as follows. And this is by induction on n. So we'll say S is 0 equivalent to T always. So this is an equivalence relation which just says, hey, everybody's related to everyone. We're all one happy family. Everybody is equivalent. And the 0 signifies I'm not really testing anything. So this is the base case of the inductive definition of this family of relations. Okay, so is everybody clear? I'm not defining one relation. I'm defining infinitely many, and I'm defining them by induction on n. So given tilde sub n, I'm now going to define tilde sub n plus 1. So we will say S is n plus 1 equivalent to T if for all A, if S can do an A action to S prime, then there exists T prime such that T can do an A action to T prime and S prime is n equivalent to T prime. And of course, we always want this to be symmetric. So I'm not going to write out as I did above, once for S and another time for T. So I'm just going to say, and vice versa. Don't forget this. because I'm not going to write it all the time, but it's always implicit there. I mean, I'm not going to write it out in full all the time, but I'll always write and vice versa. Okay, so you see, this is perfectly not circular, because once you've got zero equivalence, you've got one equivalence. Once you've got one equivalence, you've got two equivalents, and then you've got this whole family. And now we say, so remember, a relation is just a set of pairs. So of course, you can do set theoretic operations on sets of pairs and get a new relation. And now we say tilde is defined to be intersection over all n of these things, where now I'm viewing each of these relations as a set of ordered pairs. So another way of saying this is two things are bisimilar if they're zero equivalent and one equivalent and two equivalent and three equivalent ad infinitum. So this is an inductive definition, and this is Milner's definition. Okay, so is everybody clear? And this is not controversial. Let's look at our example. So let's give these guys names. This is S0, S1, S2, S3, T0, T1, T2, T3, and T4. So we're not modeling the output side. We're just modeling how does the system react to external stimuli. So S2, S3, T3, T4 are all zero equivalent. They're all one equivalent. They're all two equivalent. They're in fact bisimilar. Why? Because none of them can do anything. So that automatically means they have the same behavior, because their behavior is, I'm dead, I can't do anything. Of course, that would change if we actually took the outputs into account and said, hey, this guy's producing coffee and that guy's producing tea, but we're not doing that. So we're just saying these are dead states, they're all bisimilar. Now, S1, T1, T2, are they one equivalent? No, they're not. Because, why not? Because this guy, why is S1 not equivalent to T1? Because S1 can do a transition labeled with a capital T, T1 cannot. T2 is also not equivalent because S1 can do a transition labeled by a capital C and T2 cannot. So now we go up to S0 and T0 and we'll see, they are one equivalent, because whenever S0 can do a transition, so can T0. And whenever T0 can do a transition, so can S0. And then the places they go to, are they zero equivalent? Yes, because anything is zero equivalent. But the two things are not one equivalent. So what have we concluded? In our example, S0 is one equivalent to T0, but S0 is not two equivalent to T0. And hence, they are certainly not bisimilar. So exercise for you, not homework exercise, but just exercise, show that all these equivalence relations are distinct. So for any n, you can construct a system and a pair of states such that those two states are n equivalent, but not n plus one equivalent. Okay, the second approach. Second approach is where we have to do some lattice theory. So I'm going to postpone the lattice theory until we finish this definition, and then we'll do some pure math for a while, because you need that apparatus to formalize what I'm about to say. So let R, script R, this is the family of equivalence relations Okay, and we're going to not just view this as a set, but we're going to order it by set theoretic inclusion. So tell me, what is the smallest, in the sense of inclusion, equivalence relation you can possibly have? So smallest means fewest things are related.
We have Adam saying that nothing is related to any other thing.
That is not an equivalence relation, is it? Because one of the axioms of equivalence relation is everything is related to itself.
Yeah, Omer said only to itself, and Hanali also.
Good, that's correct. So the relationship in which everything is only related to itself and nothing else, that's the smallest element of this partially ordered set. What's the biggest element?
Maria saying everything to everything. Adam, yeah, Adam, the same thing.
Very good. That's correct. So you see there's a smallest element in this lattice of relations and a biggest element. So maybe not all of you know this word lattice, but there's going to be a kind of half-hour interlude on lattice theory coming up. So for the moment, just consider it to be a partially ordered set with some certain special structure. So this is indeed a lattice. In fact, it's a very, very special lattice called a complete lattice. Okay, so the family of equivalence relations ordered by inclusion. So there's an order relation on it. And now I'm going to define a map F, script F going from script R to script R. So if you look at the type, you see what does F do? It says, give me a relation and I will construct a new relation. So I have to tell you what this new relation is. So we'll say S is F of R related to T. So this R is a capital R. It's an element of script R. So F has said, you give me some given relation R, I will construct a new one. And this is how it's defined. If for all A, if S can do an A transition to S prime, it implies there exists T prime such that T can do an A transition to T prime and S prime is related to T prime by R and vice versa. It's easy to verify that if R was an equivalence relation, so is F of R. Okay, so this is a map from equivalence relations to equivalence relations. And what it's doing is it says, you give me a relation. What I'm going to do is I'm going to do a one-step unfolding of their dynamics. And then I'm going to ask, hey, are you now guys now related by the relation R that I was given with? Okay. So now F is easily seen to be monotone. I.e., if R1 is contained in R2, then F of R1 is contained in F of R2. And then it follows, see below, because that's one of the things we're going to prove below, that there is a unique greatest fixed point. I.e., a special relation R, which I'm going to call tilde, such that F of tilde equals tilde. So that's what I mean by being a fixed point. And if R is any relation such that f of r equals r, then r is actually included in tilde. So this is what it means to be a fixed point, and this is what it means to be the greatest fixed points. I am bigger than any other fixed point you might find. So maybe you find many other fixed points apart from this special one, but this special one is the biggest possible. We call this fixed point bisimulation. So this is David Park's formalization. Okay. Approach 3. We say R is a dynamic relation or a bisimulation relation. I use both these terms because in one set of notes I call them bisimulation relations, and the other set of notes I call them dynamic relations. I found the use of the word bisimulation relation as well as bisimulation confusing. So I was trying to lobby for the use of dynamic relation, but nobody followed me. So I'm the only one who's ever used it. Anyway, so so let's say a bisimulation relation. I would like to emphasize the indefinite article. So I'm talking about a relation having a specific property, and if it has that specific property, we will call it a bisimulation relation. And there might indeed be many. Okay, so this is the slightly confusing use of this terminology. A bisimulation relation is one of possibly many relations that have a particular property. Bisimulation is amongst those a very special one, namely the biggest one. Okay. So we say that R is a dynamic relation or a bisimulation relation if whenever S is related to T, then for every A, for every S prime such that S has an A transition to S prime, implies there exists T prime such that T has an A transition to T prime and S prime is R related to T prime and vice versa. So note, this is not circular. R is given in advance. R is given somehow, and it may or may not have this property. Okay, so is it clear that this is not circular? Because in the previous thing, I was trying to define bisimulation by saying it has this property that's apparently circular. After the thing, you still have to be bisimilar, but hey, this is the thing I'm trying to define. Here I'm saying, here's a property of R. If it has this property, we'll call it a bisimulation, and it may or may not have this property. If it doesn't have this property, it's not a bisimulation. So now we say S is bisimilar to T if there exists R, a bisimulation relate, a bisimulation relation with SRT. So this is Milner's minor modification of 2. So just some facts. So fact means things I'm not going to prove because A, they're in my notes, and B, they're very easy. If Ri is any family of bisimulation relations, then union over I Ri is also a bisimulation. As is intersection, but it's the union that's important. So in fact, what 3 is saying is that this is the union over all R a bisim. Three different definitions, easy to see. 2 and 3 are equivalent. One is not equivalent without a further assumption. So depending on time, I may or may not deal with 1, but 2 and 3 are what we use. 3 is what we use. So basically 2 looks a bit daunting for people who are not trained in math. But what Robin did with 3 was basically restate 2 in a way that people can easily understand it. But now it's time to do a digression on lattice theory. And fixed points. Quite a long digression, may take us at least half an hour. So I assume you remember what a poset is. Partially ordered set. So a set equipped with a partial order. So that's the arena in which all this stuff happens. So it's a partially ordered set with now additional assumptions. So supposing I'm in the context of some partially ordered set. We say X is a sorry, the least upper bound of X, some subset of S, if maybe this was a bad choice of letter. We'll say U. If for all X in X, X is less than U. So this is simply saying that you have an upper bound. And for all Y in S, if for all X in S, X is less than Y, then Y, then U is less than Y. Okay, so given a set, an upper bound for that set is an element which is simply bigger than everything in the set. This upper bound doesn't have to be in the set itself. It can be outside. Okay, so I didn't say that U was part of X. It's somewhere in S. Maybe it's an X, maybe not. Okay, for those of you who like Latin, this is often called the supremum. Okay, but I'm not teaching in Latin, so I'll call it least upper bound. All right, and I will abbreviate it LUB, and I'll pronounce it lub. Okay, dually, if X is a subset of S, we say V is a lower bound for X if for all X in S, V is less than X. So V has to be below everything in X. U has to be above everything in X. And V, just like U, doesn't have to be inside X. If V, in addition, satisfies, if it's greater than any other lower bound, we call it the greatest lower bound, which I'll abbreviate GLB, and I'll pronounce it glub, like a drowning man. Okay? In Latin, this is called the infimum. Now, crucial point, just because I made up a name doesn't mean these things exist. Many people are absolutely confused by this concept. Okay, I've said there's something called the greatest lower bound, there's something called the least upper bound. For a given set, these may or may not exist. Some sets have greatest lower bounds, some sets do not. All right, so is this clear? So let's look at some examples.
There's just a small question before we move on.
Yeah.
Roland is asking if you mean V is a lower bound for X, if V is less than or equal to X for all X in X, not S.
Yeah. Thank you. Somebody is alert. Thanks, Roland. Yes. Right. Just some simple examples. So one nice way of drawing of depicting posets is by drawings in which we don't put in every single arrow, but just the minimal ones to see all the relationships. So for example, here's a 3-element poset.
Okay, I'm gonna interrupt again. Just to make sure that in supremum, it should also be X, because we also have S at some point.
Crap.
We have for all Y and S, and for all X and S.
Yeah. But this one is correct. So it says if you've got any other upper bound of X, it's going to be bigger than U, because neither Y nor U need to be inside X. Okay. All right, back to this. So what is the least upper bound of these two things?
C,
Very
according to
good.
Omar and Adam and Roland.
Okay. Oh, and by the way, I could put a D here. What is the greatest lower bound of AB? It's obviously D. What is the least upper bound of AD?
Denali says A.
Very good. So here's an example where it's inside the set. There's an example where it's outside the set. In both cases, you have a least upper bound. So now let's look at this situation. So C is bigger than A and B. D is also bigger than A and B. A and B are not comparable. C and D are not comparable. What's the least upper bound of AB?
Adam is saying doesn't exist. Cole says none.
Good. No least upper bound for this. And you can see why. There are upper bounds, but there's no least one. The two upper bounds that exist are incomparable with each other. So least really means unique smallest guy, may or may not exist. So in a lattice, there is a least upper bound and a greatest lower bound for every pair of elements. These are necessarily unique. Okay? Every pair of elements. So this guy, this set of 4 elements over here, this is not a lattice, of course. And this set of 4, A, B, C, D, is this a lattice?
Cole is saying no.
Cole is saying no. Turn on your mic, Cole. and your camera.
Yes. I was gonna say, originally I was gonna say D doesn't have a least upper bound, but now I realized that it would just be D.
Well, first of all, I said every pair of elements,
Uh,
but never
then-
mind. You can still talk about the pair of elements being D, and indeed, D itself would be the least upper bound of that set. So this is absolutely, this is like, this lattice is so precious, we call it the diamond.
uh,
Okay, so that's almost like your canonical lattice. So the rational numbers with their usual ordering forms a lattice also. In fact, this is a linearly ordered set. You give me any two rational numbers, well, one is bigger than the other. So the bigger one is in fact going to be the greatest lower, sorry, the least upper bound. The smaller one is going to be the greatest lower bound. Okay, so the rational numbers form a lattice. So the rational numbers with numerical ordering is a lattice. If you add more operations, like for example, negation, you end up, or complementation, you end up with something called a Boolean algebra, but we're not going there. We just have least upper bounds and greatest lower bounds, and they're often written like this. For GLB, for LUB. And also this is sometimes called inf, and this is sometimes called soup. So these are all equivalent. Okay, so of course, in a lattice, I only asked for a pair of elements to have a least upper bound. It follows immediately by induction that any finite non-empty set has a least upper bound. Right? Because if you have three elements, well, you take the first two, take their least upper bound, then take that guy and the third element and take its least upper bound, and it will be the least upper bound for the set of three. So any finite subset will have a least upper bound. Infinite subsets may not. So in the rational numbers, if I take all the rational numbers less than square root of 2, it doesn't have a least upper bound, because the least upper bound is dying to be square root of 2, which sadly is not a rational number at all. Okay, so even Pythagoras knew that. So next definition. If L, I'm just going to write it like that, so automatically implying it's a partially ordered set and all. If L has a least upper bound for every subset, including the empty set, we call it a complete lattice. Okay, fact.
Just a quick question before. Maria's asking if any totally ordered set is a lattice. Maya, sorry.
Any totally ordered set is a lattice. Yes. Very good observation. Any totally ordered set is a lattice. But okay, so complete lattice. So you notice that for complete lattice, I only said least upper bounds. I didn't mention greatest lower bounds. So in fact, it's often defined as saying every set has both a least upper bound and a greatest lower bound, but I'm actually going to prove this is enough. it follows that least upper bounds also exist. So just a pop quiz. What is the least upper bound of the empty set when it exists? So not everything has a least upper bound for the empty set, but supposing there is a least upper bound for the empty set, what does that mean? Is a minimal, sorry, not minimal, I want to say least. So not every set has a least element. So if you, again, rational numbers, that's a lattice. It's absolutely not a complete lattice, and there's no smallest rational number. If I say rational numbers, non-negative rational numbers, so that's including 0, then there is a least element, namely 0. Okay, so there may or may not be a least element, but if there is a least element, it is the least upper bound of the empty set. Why is it like that? Well, what is the requirement to be an upper bound for the empty set? Anything is an upper bound for the empty set because there ain't nothing in the empty set. So now you have to say amongst all possible upper bounds, you have to be smaller than all of them. So this is just saying you have to be smaller than everything else. Dually, the greatest lower bound for the empty set is the maximum element if it exists. There may or may not be a maximum element, but if there is one, that is the greatest lower bound for the empty set. But there are many other things that can fail to have upper bounds or lower bounds. So for example, if I take the positive rationals between 0 and 17, or let's say inclusive, non-negative rationals between 0 and 17, including 0 and 17, this has a least element, namely 0. This has a greatest element, namely 17. But there are all kinds of sets that don't have upper bounds, even though it is a lattice. It is not a complete lattice. Okay, so just having a least element and a greatest element by itself is not enough to make you a complete lattice. You have to check that everything in sight has a least upper bound and a greatest lower bound. So as I mentioned, greatest lower bound follows automatically. So let's prove that as a quick warm-up. So proof of this fact. And now you will see why I like the phrases least upper bound and greatest lower bound, because you can deconstruct this phrase. You can use the fact that the word least is there, the word greatest is there, upper bound is there, lower bound is there. You can use those words to come up with the proof. And if I just tell you supremum and infimum, unless you're thinking in Latin, I don't see how you would use those words to help you come up with a proof. Okay, so let X be a subset of L, where L is a complete lattice as defined above. Let V be the set of all V in L such that for all X in X, V is less than X. So the set of lower bounds of x. Right? Do I know whether it's empty or not? Actually, I do know it's not empty because I know there is a least element for the whole lattice, and that guy has to be in there. But even if I didn't know that, I don't care. Maybe it's the empty set. I absolutely don't care because I'm going to be promised that this is a complete lattice, so every set has a least upper bound. Let G be least upper bound of V. Those of you who can't think in English. Okay. So I claim G is the GLB club of X. So how do we prove that? So note, for all X, so first I'm going to claim G is actually a lower bound for X, and then I'm going to prove it's the greatest of the lower bounds. Note, for all X in X, for all V in V, V is less than X, i.e., for all X in X, X is an upper bound for V. We're turning the tables. V was constructed as the lower bounds for X. Now we're saying, hey, but X is the lower bounds, is the upper bounds for V. So since G is the least upper bound for V, we have for all X in X, what did I call it? G. G less than X, i.e., G is actually in V. Since G is an upper bound for V, it is greater than any other upper bound. What's interesting about this proof is that you have the sense that almost no math happened. It looked like just an argument based on the words least and greatest. Nevertheless, I consider this to be a mathematical proof, and the mathematical properties are coded into these words. That's why I value these phrases lub and glub above soup and inf. Okay, this was just a warm-up proof. F. Supposing F from L to L is monotone. Sorry, is monotone if for all X, Y in L, X less than Y implies F of X less than F of Y. So it preserves the order. theorem. If f from L to L is monotone, and L is a complete lattice, then the fixed points of f, that means all the x's such that f of x equals x, then the fixed points of f forms a complete lattice in its own right. In particular, there is a least fixed point and a greatest fixed point. Okay, this proof, this has got a big name attached to it. It's called the Naster-Tarski theorem. And I'm not going to prove it completely. I'm only going to prove that there's a greatest fixed point. Everything in these complete lattices is very symmetric, so you can just imitate my proof and do a proof that there's a least fixed point. To prove that the collection of fixed points is itself a complete lattice requires some more thought, and I won't deprive you of the pleasure of doing it yourself. I'm highly tempted to put it on the assignment, but it's just too easy to find on the internet. And you all say, I thought of this by doing blah, blah. But anyway, let us prove the existence of greatest fixed points. All right. I'll write that here. I will only show the existence of a greatest fixed point. Okay, so we say x is a prefixed point of f if x is less than f of x. So obviously every fixed point is also a prefixed point, but there may be other things that are not fixed points but are still prefixed points, right? Now let v equal least upper bound of m, where m equals the set of all x such that x is less than f of x. So it's the least upper bound of the prefixed points. Okay. So I claim v is a fixed point. Let's prove that. So for all x in M, x is less than v. That's the definition of being an upper bound. And this v is the least fit upper bound, which implies f of x is less than f of v. Since f is monotone, which implies x is less than f of v for the reason that I've mentioned there, transitivity of the partial order, and being in M means x was less than f of x. So f of v is certainly bigger than x. So f of v is also an upper bound for M, but since v is the least upper bound, for M, we have v less than f of v. Whoops, how did it get so fuzzy? Now, I said, okay, so this is the end of the proof. Sorry, this is not the end of the proof. We have v is less than f of v. So v is actually in M. V is actually in M. Very interesting. So now v is less than f of v. Apply f again. So we've got f of v is less than f of v. So f of v is also in M. Right. But v is an upper bound for M. So f of v has to be less than v. So together this implies f of v equals v. Now, any fixed point is in M. So the prefixed points, of course, include the fixed points. And I've just said v is bigger than anything in M. So v is bigger than anything in M. So v is the greatest fixed point of F.
We have a question. Omar is asking, doesn't the inclusion of V and M follow from monotonicity of F?
Yeah. What do you mean? It doesn't follow immediately. I have to give an argument. I mean, one can say, oh, this thing immediately follows from monotonicity of F. Yes. It doesn't immediately follow. You have to say something. So what do you mean? Doesn't it follow from monotonicity? Who said that?
He just said, never mind.
I mean, yes, it does. There has to be some justification. Don't write your homework like that. Hey, this immediately follows. Okay. Back to, So to prove that there's a least upper bound, you can mimic this proof word for word with the things reversed. Instead of looking at the prefix points, we look at the postfix points, the ones such that f of x is bigger than x. Sorry, such that f of x is smaller than x. And then you ask for the greatest lower bound of that set. And then you can prove that that is the least fixed point by exactly mimicking this argument with the right things changed. To get that you have a complete lattice of fixed points requires a bit more cleverness. But let's go back. Let's go back to back to what? Okay. So note to be a bisimulation relation. Actually, before I say that, oh, all I need is for the thing to crash on me and lose it. To be a bisimulation relation means R is contained in f of R. So this is a complete lattice. The power set of any set is a complete lattice, but many other things are also complete lattices. So the collection of all equivalence relations on any set is also a complete lattice. F from R to R is monotone. And now least upper bound of the set of all R such that R is a bisim which is how do you compute least upper bounds in set like lattices like this? You just take the union. So it takes the union of all R such that R is a bisim. And this is greatest fixed point of F. Okay, because this is what we just did in our proof. We found that if you take all the things that are prefixed points and take their least upper bound, you'll exactly get the greatest fixed point. So this shows 2 and 3 are really the same thing. So there's a fixed point characterization of bisimulation, and there is a way of rendering that by saying just look for an R with this property, and if you can find such an R, that proves that things are bisimilar. Now, one is not the same unless the transition system has a special property. And here's the special property. For every S, for every A, the set of T such that S has an A transition to T, the set of places you can get to from S is finite. So even though the whole transition system might be infinite, but from any state, maybe you can jump to many places, but only finitely many. You can't jump to possibly infinitely many different places. That particular property is called image finiteness. And the claim is, if the transition system is image finite, then one, so Milner's original definition is equivalent to 2 and 3. The definition of bisimulation is an example of a co-inductive definition. So it's not an inductive definition. So the way Milner presented it, it looked like induction, and the family was defined inductively. But if you look at what he did overall, it wasn't actually induction. It's something exactly the opposite of induction called co-induction. So let me just say this in words rather than writing it down. How do you normally think of an inductive definition? So you say, look, I have some base cases, and somebody did point out right away, hey, there's no base case here. And actually, we haven't made it properly inductive because it ain't. And there is no base case. It's co-inductive. So what do you do in induction? You say, I'm trying to build up something inductively, maybe terms in a language, maybe lists, maybe something. And you say, I have some base cases, and then I have some rules for building up new things from the base cases. So I first say, I apply my rules to the things in the base case, and so I get some new things. Hey, but then I can apply my rules again to the new things I just constructed. I get yet new things, and I keep throwing them in. So you start out with nothing, then you add in your base cases, and then you start constructing new things. So every time you're getting a bigger and bigger set. And in the end, what do? You take the union of all these things. And this is the completion of your inductive definition. So for example, if I'm defining finite lists, and I say lists of A and B, or words over the alphabet A, B, I say, well, the empty word is a word. And then I say, if I've got any word constructed with A and B, and I stick an A in front, I get a new word. And if I stick a B in front, I also get a new word. So then I say, right, initially I have nothing. Then I say, okay, wait, empty word is a word. Then I say, okay, let me apply my construction rule. I stick A in front and I stick B in front. Now my set of words is A, B, and empty. And then you say, wait, I can do this again. So now I've got A, B, B, A, B, empty. That's my, and I keep going like this, and I get longer and longer words. In the end, I take the union. I've got all finite words constructed from A and B. Is this clear? How induction starts from an empty set and keeps growing it, and in the end takes the union. It's exactly the opposite thing that we said for bisimulation. We said everybody is related. That was our tilde sub 0. Then we said, oh, no. We're going to take all the guys who are related already and throw out some. And then in the next step, we're throwing out some more. And then in the end, instead of taking the union, we take the intersection. So every step of what we do in induction is mirrored and reversed. And in the end, you cut it down, and what you get is bisimulation. So it is a canonical example of what's called co-induction. Those of you who've studied stream programming will see that lists are built up inductively, streams are constructed co-inductively. And in fact, there's a perfect mirror image between these two theories. Okay, so that was my co-inductive propaganda. We're going to take a short break, 10 minutes. We come back at 12:23, and then I will prove logical characterization of bisimulation.
I have a homework question.
Yes.
So for the
Assignment 2.
yes,
Just 1 second. I'm just reading a message from my sister.
okay.
Okay. I guess she's all right. Yes, sorry, Maria, what was your question?
Alright. So for question 5, where we are supposed to show which pairs of formulas of temporal logic are equivalent.
Mhm.
So it says that in case they're not equivalent, we need to give a transition system which shows that they're not. But is such transition system just like as informal as like the street lights example, or how exactly?
I want you to draw circles and arrows,
Okay.
small ones. So two of them are in fact not, two pairs are not equivalent, and no example has more than 2 or 3 states, maximum 3. So
Okay.
please don't draw me a 35 state system to show me that they're not equivalent.
Okay. And then yes, for question 8, I'm just having trouble with this question that it's proving identities, because like I don't know how formal we should
So
have
what is this question about? It's proving identities between what and what?
omega regular expressions.
So you can just do that by reparsing.
Okay,
You can
so
argue semi-formally, or, informal doesn't mean imprecise.
okay,
So it's informal, but still I want a precise answer. So you can
okay,
say any word like this can be rearranged so that it looks like it's from that, and that proves that they're equivalent.
okay, sounds good.
And of course, you're not yet ready to do 6 and 7.
Yeah.
Let me just check my mail. Can you guys see my mail? No, because I'm not sharing that screen.
No.
You never know what might be in my email. Recommendation deadline. So the summary I get is recommendation dead. Okay, recommendation deadline. All right. Record a video of the presentation, which we learned. Marcel has given me a score. Very good, Marcel. Oh, yeah, well. Dear invited speakers, I'm not an invited speaker. Something rubbish starts in 20 minutes. Faculty meeting, delete. Etsy, delete. delete, 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 eBay, delete. Okay, nothing exciting. Let me check Skype. Who was the co-host? I've forgotten.
Marinique.
I guess she's not there. Was there any interesting thing happening in the chat, Maria?
We were just discussing Gomar's comment.
Omar, you look like a Roman emperor being taught lattice theory. Quickly switches off his camera.
In the last proof, we could have also used Zorn's lemma, right?
This is equivalent to Zorn's lemma.
Okay.
But why use Zorn's lemma when you have a direct proof like this?
Yeah, I mean, I just thought it looked familiar.
How would you use Zorn's lemma exactly?
Because Zorn's lemma says that if we have the partially ordered structure such that every finite one has
No,
every
not every finite one. Every ascending chain.
every ascending chain has an upper bound,
Mhm.
then the entire structure has an upper bound.
No, sorry, you're misremembering Zorn's lemma in some crucial ways. So first of all, it says every chain has to have a least upper bound, not just an upper bound.
Yeah.
And then it says not that the whole set has an upper bound, the whole set has a maximal element.
Yeah, that's
It's very different, and in a very important way, because maximal element is very different from greatest element.
okay.
You can have many maximal elements that are not comparable. Okay, so I think you're thinking that this is like immediate from Zorn's lemma. It's not. And maybe because you're misremembering Zorn's lemma that you're thinking that.
Okay.
Wait, sorry. Zorn's lemma? I thought Zorn's lemma only required upper bounds, not least upper bounds.
Every,
that's
sorry,
Yeah.
you're right. Every chain has an upper bound, but then the conclusion is that the set has a maximal element,
Yeah.
not a greatest element. So to prove that there's like a greatest fixed point, I'm not so sure how exactly you would do it by Zorn's lemma. And where are the chains coming from anyway? Because a set of fixed points doesn't form a chain, right? There might be incomparable fixed points.
Yeah.
What's yellow and maximal?
Hmm.
Zorn's lemon. Old math joke. Like, what's purple and commutative? An abelian grape.
It's gonna be in the recording.
Oh no!
There's a follow-up to the grape joke, but I forgot how it goes.
Okay, 12:23, one more minute. But yellow and maximal is an old joke, Hanali. Everybody knows it. I see Omar has gone out of his Roman emperor pose. Now sitting at attention at his desk.
that's not my desk.
Oh yeah?
Yeah,
You have a fake background.
exactly.
Ah,
I could just be doing anything. For all you know, I'm sitting out in my backyard.
Uh-huh. Okay. So to prove the equivalence of 1 with 2 and 3 requires essentially a kind of continuity argument, except that it's, so to speak, the opposite of continuity, and it's called co-continuity. And so I've given you 2 handouts. One was a long 14-page handout, which was written for Comp 330 students, all very elementary with a lot more gas about modeling. And then I gave a short 5-page handout, which I wrote many years ago for a grad course. So that second short handout contains the proof of the equivalence of 1 with 2 and 3 exploiting co-continuity. So if you're interested, you can read it, but I don't think we have time to do that because I want to do something important, for which I have only like 30 minutes, which is the logical characterization of bisimulation. Logical characterization of bisimulation. So, given a transition system, which consists of a set of states, a set of actions, and a labeled transition relation. So maybe we should call it a labeled transition system. We define a modal logic. So this is a bit like temporal logic, but it is not exactly the same. It's adapted to the transitions. We define a modal logic called Hennessy-Milner logic. So what's in this modal logic? I'm going to give in our syntactic notation the inductive definition of the terms. So true, let me see, what did I put in it? Okay. Negation. So implicitly I've got false also by negation of true. Phi1 and phi2. So if I've got 2 formulas, I can take their conjunction. And of course, you now know I can take disjunction also if I want, because I've got negation. And I've got a diamond, but except this diamond, unlike the temporal logic diamond, has a letter A sitting inside it, where this A belongs to the set of actions. Okay, so the semantics of all these things are obvious to you, and it's obvious to you that I could define or if I wanted, or implication or whatever, but I want to give you the semantics of diamond and then mention another derived operator which I won't use. So as before, we will say a state satisfies a formula. Okay, so all states satisfy true. A state satisfies not phi if and only if it doesn't satisfy phi. The state satisfies phi1 and phi2 if and only if the state satisfies phi1 and the state satisfies phi2. And now we come to the modal formula. S satisfies diamond A phi if there exists T such that S can do an A transition to T and T satisfies phi. Okay, so remember this means can do. not must do. So it's possible that from S, if you do an A, you'll end up in a state which doesn't satisfy phi. But as long as you do end up, one of your possibilities is a state that does satisfy phi, we'll say diamond A phi. We're also going to define something called box A phi. And this says not diamond A not phi. And this means every state T such that S can do an A transition to T must satisfy phi. Okay, so sometimes this is read as may A phi and must A phi. Okay, so this is called must, and this is called may. But must is really not necessary because you see it's defined as the De Morgan dual of diamond. So we'll only concentrate on diamond. So let's look at some example formulas. Let's see, what are some good examples? Okay, so let's look at our old examples. I'll just call these A's and B's now. So let's look at what formulas these things satisfy. So S0 certainly satisfies diamond A true. And this just means I can do an A and end up somewhere. I don't care where, because after that, I'm not checking anything. So notice, however, that Q1 does not satisfy diamond A true. In fact, in Q1, you can't do anything. Okay. So if you rewrite this, this is the same thing as saying Q1 satisfies not diamond A true, but that's the thing, same thing as saying box diamond A false. So how do you read that? Every A transition you make from Q1 must end up in an impossible state, because no state can satisfy the atom false. That means basically you can't be doing A transitions. All right, so notice there's negativity in this logic. You can write negative statements. Okay, tell me more interesting formulas. So S0 satisfies diamond A, diamond B true. Also, it satisfies diamond A, diamond B true. T0 satisfies diamond A, not diamond B true. Because it's possible for T0 to go to a state, namely T2, by taking an A transition and end up in a state where it cannot do a B. So basically it says from T0, it is possible to take an A transition to a state where it cannot do a B?
We have Haneli asking if it should be diamond C.
Where? Haneli, turn on your mic. I don't, let me,
It's S0 satisfies A and B, it's written twice. I think you meant A and C on the right side.
correct. The second time. Yes, thanks. Okay, so you see that S0 and T0 satisfy different formulas. And indeed, S0 and T0 are not bisimilar. So here's the theorem. S is bisimilar to T if and only if for all formulas S satisfies phi if and only if T satisfies phi. So this is what we mean by logical characterization of bisimulation. So the whole process of bisimulation can be couched in terms of satisfaction of logical formulas. And in fact, if you ask me, how do I prove two things are bisimilar? Well, the definition says, look for an R that has the bisimulation property. And if you can find an R that relates the two states in question, you've done. And what if you say, prove to me that these two guys are not bisimilar? Well, then, what can you say? Gosh, I kept trying to find an R and I failed. Well, that's not a proof that it's not bisimilar. But now you have a proof technique. You say, aha, I'll show you a formula on which they disagree. And if they disagree on a formula, they cannot be bisimilar. Okay. So I think I give examples of this in my long notes, but in the short notes, I actually do the proof. And how are we going to do this? We define a new equivalence relation. Which I will write with a double tilde. You say S is logically equivalent to T if and only if for all formulas of the logic, S satisfies phi if and only if T satisfies phi. And the idea, prove that this is a bisimulation relation. So if I prove that that's a bisimulation relation, that immediately implies that if two things are satisfy this logical equality, they must be bisimilar. Okay. What about the other direction? So the other direction, you have to show if two states are bisimilar, then they must agree on all formulas. And that's an easy induction on the structure of formulas, and I'm not going to do it. It's in those notes. Okay. Now, I forgot to mention one important point. This is for image finite systems only. Finiteness assumed. Okay. If systems are not image finite, then it is false. You need to enrich the logic. You need to put infinite conjunctions in the logic. Okay, so don't be scared of infinite conjunctions. There are all kinds of logics where you have infinite conjunctions and things happening. Okay, but ordinary undergraduate logic, it won't fly unless you have image finiteness. So I'm going to assume image finiteness and prove it. Okay, good. Now, suppose S is logically equivalent to T. And suppose S can do an A transition to S prime. So I want to show there exists T prime such that T can do an A transition to T prime and T is logically equivalent to T prime. Sorry. S prime is logically equivalent to T prime. Okay, and of course, symmetrically, the other direction will just follow by the same argument. Okay, so sadly, this is going to be a proof by contradiction. So assume that S and T are not bisimilar. Okay, that means, what does it mean? So bisimilar said, anytime S can do an A transition to S prime, then there exists a T prime. So now I'm going to say for all T prime, it doesn't match up, i.e. for all T prime such that T can do an A transition to T prime, S prime is not logically equivalent to T prime. And here is the key point. There are only finitely many such T prime because of the image finiteness assumption. Okay, so enumerate them T prime 1 up to T prime n. Okay. For each T prime I, there exists a formula phi of I such that S prime satisfies phi of I and T prime I does not satisfy phi of I. So you might say, wait a minute. Maybe it's S prime that doesn't satisfy the formula and T prime satisfies it. But of course, I've got negation in my logic. So I can just take the negation of that formula, and without loss of generality, I can take this. So now consider the conjunction of all the phi i's from 1 to n. So S prime satisfies this phi, right? Because each of these things was taken to be some formula that S prime satisfied. So it satisfies that conjunction. But none of the Ti prime satisfy phi. because they must be violating at least one of them. And means you have to satisfy all of them. Okay, but this means S satisfies diamond A phi, but T does not. T does not satisfy diamond A phi, and this is a contradiction since we assumed S and T satisfies exactly the same formulas. Okay, so from this contradiction, we conclude, therefore, the assumption that S prime is not logically equivalent to T prime for all T prime such that T has an A transition to T prime is not correct. So there exists some T prime such that T indeed goes to T prime and S prime satisfies all the formulas of T prime. Thus, this thing is a bisimulation relation. Thus, S logically equivalent to T implies S bisimilar to T. And we are done with our grand theorem. Okay, so to show is an easy induction on formulas. So I have 9 minutes left in which I'm going to spend shamelessly bragging about how great I am. So let me just make some remarks about probabilistic bisimulation. Which I'm not going to define. I'm just going to tell you historical ramblings about what happened in the probabilistic bisimulation case. So I am going to shamelessly brag about how great I am. What am I so great for? I am great because I attract the absolutely most brilliant students. And one of these absolutely amazing, brilliant students is now a full professor at University Laval. Her name is José Dearnay. Actually, I didn't attract her. She fell from heaven and wound up in my office. That's how I feel anyway. So basically, she she proved this theorem mainly. I was mainly the cheerleader, saying "Go, Jose, go." But anyway, here is what happened. So for probabilistic bisimulation, you are looking at probabilistic transition systems. And with probabilistic transition systems, you, instead of just saying, oh, I can go here, I can go there, you say, if I do an A action from this state, there's a probability distribution about where I can end up. So I call these things labeled Markov processes. And except for the absence of rewards, they're basically MDPs. So extending this to MDPs was, I would say, an absolutely trivial step. All the machine learning people get up and jump up and down and say, oh my God, this was invented by a couple of machine learning guys, because of course they all think that only machine learning people do anything. But in fact, those two machine learning people, they cite the papers from the verification world. It's just that the other machine learning people don't. Anyway, so probabilistic transition systems. So to study the logical characterization, we looked at a slightly different type of formula. And this says the probability. So A was an action, but Q was a rational number between 0 and 1. The probability of winding up in a state satisfying phi after doing an A action in state S is greater than Q. And actually, it doesn't matter a lot whether you make it greater than or equal to. For either definition, the theorem works. Now you look at how we did this proof just now. We crucially used the fact that it is image finite, so that there are only finitely many states you can go to. Okay, so if you have only finitely many states, you can kind of analyze each state and look at a formula for each state, and then because there are only finitely many, you can take the conjunction. So Larson and Scow proved logical characterization using this logic. And negation and conjunction. So once you've got negation, you've also got kind of the box version. Then they did variations where they said, okay, we won't let you have negation, but we let you have the atomic false, and we let you have box, and we let you have disjunction, and so on. So they did some variations, but every one of their logics involved some kind of negation. Also, they assumed a very strong finite branching assumption. So they assumed not only that in every state the branching is finite, but in fact it's bounded. There's some fixed number like 17, and you cannot go to more than 17 states. Whereas in the other proof, in this state, you may have 17 and that one 18 and that one 19 keeps growing. But there they said, no, there's some uniform bound. And then most importantly, they said all the probabilities that appear in the description of the system, they all have to be multiples of some fixed rational number, integer multiples of some fixed rational number. So it's a very, very restricted thing. Okay. So then Desharnais et al. So in case you're wondering who Al is, that's Idalat and me. We were considering continuous state spaces. So not just infinite, but like the real line or a manifold or something. And then to say finite branching, that's a joke, right? I mean, if you want to talk about things like diffusion processes or things that are jumping around in the real plane, no way is it going to be finite branching. If it's going to be finite branching, you might as well take those countable states and take it out and say, it really wasn't in a continuous space. I just had an embedded, had a discrete system embedded in a continuous space. But we wanted genuine continuous spaces. So no finite branching. And basically people believed it's not going to be possible to do a logical characterization theorem. But then, amazingly, we were able to prove logical characterization with no finite branching assumption, and more dramatically, or equally dramatically, no negation in the logic. And basically, the reason we were able to do that is because we didn't copy this proof and adapt it to the probability case, which is what Larson and Sco did. We used entirely different tools coming from measure theory and special properties of a kind of space called an analytic space. And so I would say this was really a startling result, okay, because no negation in the logic. Well, all those discrete systems are special cases of our continuous ones. So we've also improved the old result because we've done logical characterization now for discrete systems without using any negation in the logic. And in fact, because there's no negation in the logic, we also got logical characterization of simulation, which I haven't defined for you. But it's kind of the one-directional version of bisimulation. Bisimulation is they can both do the same things. Simulation means I can do everything you can do, and maybe I can do more things. So we proved a logical characterization of simulation as well, which you can't do if there's negation in the logic. So these were pretty startling results. And the first time Jose presented it, it was kind of at a summer school, and she got a 10-minute slot for student presentations. And usually the student presentations were, I'm trying to learn this, or I've done that, or I've done this tiny little thing that I'm working on. And she comes and announces this sensational result. And all these, big shots in the audience were there. Samson Abramsky, Davide Sangiorgi, they're all very nice and polite. And and of course, she's this shy young student whom who they're trying to encourage. So they said, yeah, this result that you're saying can't possibly be right, because we know it's well known that there are counterexamples to this claim. You must have negation in the logic. And in those days, she didn't speak English so fluently. So she just turned around and, sometimes when you don't speak a language well, you don't always say things as smoothly as you intend. I find this when I'm speaking French a lot. So she turns around and looks at them and says, "Be quiet. At the end of my talk, you will have no more doubts." And then she turned back and gave the proof, and they were indeed, they were like, wow. So yes, anyway, end of bragging. Tomorrow I will do machine learning. After ragging on machine learning people today, I will do learning automata. And then in the second half, so that should only take the first half. The second half, I'll talk about how to extend temporal logic with fixed points. So now you know some of the mathematics of fixed points from lattice theory. So I couldn't do this yesterday, but now we've got the toolkit to add fixed points to our temporal logic and make it much more powerful than it used to be. Okay, I will stop the class and more importantly, stop the recording before I record any more embarrassing statements. Hello, how do I stop the recording? All right, more.